Okay, so we're gonna get started. Hello and welcome to Diggin In. I'm Lindsay Randall, the host of the speaker series. And Diggin In is a series of live presentations with archaeologists from around the country, co-sponsored by the Robert S. Peabody Institute of Archaeology and the Massachusetts Archaeological Society. Join us every other Wednesday at 1:30 p.m. Eastern Standard Time through November for our presentations. For a schedule of dates and presenters, please visit us at peabody.andover.edu or at the Massachusetts Archaeological Society's Facebook page. Viewers are able to submit questions directly to me via the chat function on the side of your Zoom screen. And at the conclusion of the presentation, we will give our speaker time to answer as many questions as they can, with the understanding that we might not get to them all. And today we are excited to have Dr. Kate Johnson joining us. She is currently a research associate at the North Carolina Institute for Climate Studies, based at NOAA's National Centers for Environmental Information in Asheville, North Carolina, where she performs GIS and web duties in support of the National Climate Assessment. In addition, I will say Dr. Johnson is one of the UMass Boston graduates that I went to school with, so I'm very excited to be able to work with her today. So welcome, Dr. Johnson, and thank you for joining us today.
Thank you, Lindsay, for that nice introduction. And wow, thank you everyone for coming. It's so nice to see some old friends and nice to see some new faces as well. I'm really excited to present today to you guys, so I hope that my screen sharing works. I also wanted to say that this is my first Zoom presentation, so I apologize if anything weird happens. I will try my best to guide you through. And now I will attempt to share my screen. And it looks like it's working. So thumbs up if you see PowerPoint. All right, okay. Okay, so I am going to talk to you today about applications of light detection and ranging, or LiDAR, for archaeology as well as historical land use studies. Some of you know me, I know that I worked on this research for my dissertation, which I got at UConn, my PhD dissertation, I received my PhD from UConn in 2016. I've continued working on this research, and most of it is focused on southern New England, mostly Connecticut, and some locations in Massachusetts and Rhode Island. So I'm going to give you a brief overview of how LiDAR works, and then I'm going to kind of give you some examples of things you can see in it, and how to interpret it in various studies that you can, or various ways that you can use it for historic land use studies. So now I will see if I can advance the slides, and I can, so good. So LiDAR stands for light detection and ranging, and if you're familiar with sonar or radar, it's very similar. Radar is radio detection and ranging, sonar is sound navigation and ranging, and LiDAR is light detection and ranging. So the difference is that it uses lasers instead of radio waves or sound. LiDAR was developed in the 1960s for satellite tracking and military purposes. It was used in the 70s to measure the topography of the moon's surface by some of the Apollo missions. Geez, I'm having some trouble advancing my slides. All right, got it. And then it's been used in meteorological applications since the 70s. You can see here, this is actually cloud measurements from one of NASA's satellites. And then recently it's been used in self-driving cars to measure speed, and then various states have collected their own LiDAR data sets, some for flood studies and other uses. But since the early 2000s, it's been used in archaeology. There have been various case studies all over the world, and some even in New England. Some notable ones have been in Cambodia, South America. Some of the examples here are Mayan temples and structures in Belize, a deserted medieval village in Italy, and then in our very own backyard in New England, an abandoned farmstead in northeastern Connecticut. So there have been a lot of since, you know, the early 2000s is like 20 years ago now, if you can believe it, there have been a lot of advances in visualization techniques to try to identify various types of cultural features. And the current trend is kind of towards big data and machine learning to automatically extract various types of features from the landscape. So how does LiDAR work? LiDAR is a laser scanning device that's attached to an aircraft, and the position of the aircraft is well documented as it flies. And as it flies, the laser scanner emits pulses of light in the near infrared part of the spectrum. And the pulses are emitted at such a high rate that they can actually fit down in between small little spaces in between the branches and leaves of trees. So they can actually get down as far down to the ground surface. Once the laser pulse interacts with features on the landscape, it then returns to the device on the aircraft. So every interaction creates a point, and a three-dimensional point cloud is then created from all of these interactions. And then the point cloud is actually classified based on what the objects are eventually. So here are just some examples of profiles of LiDAR point clouds. So in the top, it's a residential area in Ashford, Connecticut. This is actually a house that I was renting with roommates while I was at UConn. But you can see the dark green is the first return that the LiDAR, the laser beam hit and returned back. And then yellow, orange, and red are later ones. So you can see that the ground surface underneath the tree, the returns are actually 3 or 4, so that you're not going to get a first return hitting the ground surface in an area that has a lot of vegetation. But you can see in the second one, and even in the agricultural one at the very bottom, that there are more points and more hits on areas that are wide open. So in the forest, it's actually more difficult for the laser beam to kind of get down onto the ground surface. And that's why the returns, you know, it's the third or fourth return. So from this point cloud, you can then create digital elevation models and digital surface models. So a digital elevation model will be points only on the ground. So this red line here on the profile. So points that are only classified as ground are used in a digital elevation model. And what happens is there's an algorithm, various algorithms actually, that you can use to interpolate between the points and create a flat surface. That surface can then be hill shaded, which is basically a process of approximating the sun's light at various angles on the topography. So in this case, that is the most common way to kind of visualize these topographic plans. If you use all of the returns in the point cloud, you can create a digital surface model. And that is created by using, if you see this blue line here, it'll get the tops of the trees. And you can do a difference between the surface model and the elevation model if you were looking for information such as canopy height, for example, if you wanted to see how tall the trees were. So those are kind of the two most common products that are used. In this presentation, I'll mostly be using digital elevation models. And then interpreting the data, knowing the resolution of both the point cloud and the digital elevation model is very important in how you, what sorts of features you are looking for and kind of how you interpret the entire landscape. So this is an example of a building foundation that I've taken a profile of in the point cloud and in the DEM. And you can see that depending on the pixel resolution of the DEM, you can get very different results in how it looks. So for example, this particular LiDAR point cloud, I believe is about 2 points per square meter. So you can generate a fairly high resolution DEM from that. And so at the top, you see that I've created one that's about 25 centimeters. And you can see the outline of that building foundation pretty well. But when you go to 2 meter pixel resolution, you can't really see it. And so so for example, if you had a 2 meter pixel resolution on your DEM and you had a feature that was smaller than 2 meters, you would not be able to see that feature. So understanding the resolution is really important when you're trying to figure out what sorts of features you can see, and understanding those types of things. The point spacing and vegetation is also an important consideration. On the right or on the left of this, we see points that have been classified as ground. And notice that there's a large gap in the amount of points in an area that is really densely forested. So in this case, the laser was not able to get down to the ground surface. And what would happen is when you ran that interpolation algorithm, there would have to be quite a lot more interpolation between those points, and so you might not be able to see features there. It's also really important to use a lot of complementary resources when you're trying to analyze LiDAR. Aerial imagery, modern aerial imagery, historic maps have been really useful in trying to do that. In New England, field work is also really important to make sure that the features you're seeing are what you think they are. In this case, this is Middletown, Rhode Island, and there are actually Revolutionary War earthworks that were here, and it's in the middle of like a residential neighborhood. But it's really interesting because there are lots of historical maps that kind of show where they are, but everything else around it is just residential streets, except for this one earthwork, which is pretty interesting. So once you kind of have all that stuff down, and you have all of your information, and you're kind of ready to work for it, ready to look for things, you can start doing that. So here we have a modern aerial photo. We can see that it's all forest. And then when we look at the same area with the LiDAR DEM, wow, we can see that there are walls everywhere, and there are abandoned roads, and there are even building foundations. We can start mapping these things in GIS. And we've been doing it manually, but there are a lot of neat papers out that kind of talk about automatically extracting these features based on their properties. So that is definitely the way of the future, I think. And then if you look at, this is a aerial photograph from 1934, you can see that it was indeed a farmstead at one point in time. You can see the buildings, you can see the cleared fields, and then some of the other fields that are a little bit, they're successional with various, I think white pine is the species that comes in first in Connecticut, maybe most of southern New England. So it's really cool to be able to compare, that area with historical aerial photography. Now I'm going to talk a little bit about, as you can see, the impacts to the landscape are great, and it's not always visible. So I'm going to give a little bit of background on this proposed geologic epoch called the Anthropocene. So this is basically the idea that humans have had great impact on the environment and landscape, and the timing varies, but we know for sure that this goes back to at least the advent of agriculture, and even possibly the megafauna extinction in North America. And so it varies. The timing and the impacts vary all over the world, and in New England, we know for sure that there was clearing for agriculture by Native American groups, especially in coastal areas prior to the arrival of European colonists. However, the arrival of English colonists in New England really changed the landscape in such a dramatic way. Deforestation was really, really profound and changed all the geomorphology of the rivers and sedimentation. It was quite dramatic. And so a lot of the features we can see today, especially the walls, are related to this kind of turning point in the landscape history in the region. So I've just added European colonialism, 17th century, to this chart, so we know where it stands in relation to everything else. And I'll talk a little bit about how dramatically this English-style agriculture changed the landscape. So it was fundamentally different from what was already there from various Native American groups. It involved this widespread deforestation, which hadn't really been quite so dramatic before. And also this concept of improvement, you know, making the land better for specific types of planting and agriculture. A lot of plowing, a lot of drainage, and also well-managed woodlots were part of that. The peak of this clearing was about 1850, and it would have been a landscape that was cleared and opened and dotted by stone walls and fences. But then in the 19th century, we actually see this widespread farm abandonment. And this was caused by industrialization, a lot of population pressure from those on children and those original farms, and then westward movement. You know, and so you can see this is actual data from the agricultural census showing the change in improved land from 1850 to 1890. And we can see in these kind of core areas that had been settled by the colonists first, we see an actual loss in improved land. And then a gain in improved land in areas that had been settled a little bit later. So this process of abandonment is really interesting, but it caused a lot of these, you know, cleared landscapes to end up in the forest like we see them today. One of the other processes that's not really talked about a lot, especially in Connecticut, is the iron industry. So northwestern Connecticut was called the Salisbury Iron District, and iron ore was discovered in the late 1700s in that region, or maybe it was mid, anyway, the 18th century in that region, and it was settled, but there was widespread deforestation in northwestern Connecticut to produce charcoal to fuel these furnaces. Coincidentally, the peak of iron of production in iron furnaces in Connecticut was about 1850, which it coincides with the peak of loss in forest cover as well in Connecticut. And iron production occurred, you know, from Vermont all the way down to Georgia, along the Appalachian Mountains, and in Pennsylvania. It's been really well documented as well. And this is an example of what an iron furnace might have looked like, or what it did look like. So a couple relict land use features that are results of these types of land use are, of course, stone walls, one of the iconic features of the New England landscape. Now we see them mostly in the woods, but that's not how it always was. This is an example of what they look like in the LiDAR data. And then a photograph showing clearing a field with a stone boat. And then for charcoal hearths, another example of what they look like in the LiDAR data, they're round platforms that are kind of cleared out cut out from the surrounding slopes. And then colliers would have taken the wood and stacked it and covered it with soil and let it smolder. Then they would have harvested the charcoal and sent it to the furnaces in order to produce the iron. But there are thousands of these features all across the landscape. And these have been documented in Pennsylvania as well. Another feature we see are building foundations, like I mentioned. So here's an example from Connecticut. This one is in a cross section of what it looks like in the point cloud. You can clearly see it, although, you know, like I mentioned, some of the returns, it took a little bit of effort to get through the forest canopy there. And I will mention here that a lot of LiDAR flights that seek to map the ground surface instead of actual forest structure are flown in seasons where there are no leaves on the trees, in places where that is possible. Other features we see are sawmills and earthen or stone dams. So here's an example from Tiverton, Rhode Island, where we see the large wall there, and I believe this is in Mansfield, Connecticut, but another example of an earthen dam there. And so once you start finding them all, you can start mapping them. This is just an example. I think it's pretty old at this point. We've done a lot more. But the blue dots are those charcoal hearths I was mentioning. The red lines are stone walls, and the yellow squares are building foundations. And this is a subsection of an area in northwestern Connecticut. And these are only 3 types of features. The reason we've picked those 2 is they're the most indicative of deforestation. So part of the work we've been doing is trying to reconstruct historic forest cover. And they're the easiest to use and most relevant. So you can also take a look at with archival materials. This is an example of a really beautiful survey map from Westport, Massachusetts, available from the Westport Historical Society. And then what you can do is georeference it, which is what we did. And if Krista will probably recognize this. And so what you can do is it matches the stone. These are the stone walls from the LiDAR data, and you can see that they actually match the map's boundaries very well. So these are actual boundaries from 1712 that persist on the landscape today. And then if you pull up modern parcel boundaries, you can see that they match pretty well also. So it's interesting to look at the persistence of these boundaries on the landscape and try to, get a sense of the actual time and the sense of history that this provides. You can see the same thing in the next town over in Rhode Island, in Little Compton. There's a map on the right from the 1690s that shows some of the original lots from the late 17th century. I don't remember the size of these lots. If Marjorie O'Toole is on the line, she could probably clarify that. But on the left, you can actually see these lots, these long strips of land on the coast in the LiDAR data, which is really interesting. So I'm really interested in this persistence of boundaries through time and how you can still see them. You can also map stone wall density. So this is again in northwestern Connecticut, we've mapped the density of stone walls. In some cases, it reaches almost 12 kilometers of wall per square kilometer. So that is very dense. That is a lot of wall. And we wondered, well, what else can we do with this aside from saying, well, that is a lot of wall? Well, we've started comparing it to the US Census non-population schedule for agriculture. And so this is a really great resource. It was taken in 1850, 60, 70, 80, and 90, I believe. And that was that map I showed you before to talk about abandonment, excuse me. And so with improved land, it was for every farm, they would take improved land, unimproved land, and in some cases, in later censuses, it was broken down into a lot more specific categories, as you can see in the 1880 screenshot there. But improved land was basically anything that was tilled, pastures, meadows, orchards. Unimproved land was forest. And then if there were any old fields that had started growing up and started being successional, those were probably also included. We did add those totals up for every town that we studied, and sometimes they did not equal the actual area of the town. So this kind of suggests the presence of other land use types, maybe unsettled areas, or even water bodies that might not have been accounted for. In any case, the differences weren't very much. So most of the land seems to have been accounted for in these censuses. So if we do the comparison, on the top we have stone walls in those three towns in northwestern Connecticut, and on the bottom we have relict charcoal hearths. If we do the density again, so in this case we're using a threshold of areas that have walls greater than 3 kilometers of stone walls per square kilometer, and 2. So if we compare that with the census data, we actually get an R-squared value of 0.98, which is really good. Taking the area of really dense stone walls and areas calculated from the census, that is the comparison that we're doing. And then if we do the same thing for charcoal hearths, areas where there are greater than 15 charcoal hearths per square kilometer or greater than 10, and then compare that to unimproved land, we also get fairly high R-squared values. So this is basically saying that these relict land use features are very good proxies for reconstructing past forest cover and kind of looking at how it relates to this archival data and kind of proving it right. But these features also kind of give you a story of cumulative land use over time, as opposed to just a snapshot of a specific year. So the walls are telling you this is all the land that has ever been cleared in this town. So you can do really interesting calculations with this. And this is all from a paper that we just submitted. So hopefully we will be getting published pretty soon. So to kind of finish up, LiDAR data is available pretty much everywhere now. And I've just told you what to look for. So as it becomes so available, and as people are kind of finding all of these cultural resources, how do we take care of them? What do we do to make sure that they stay, for all intents and purposes, safe? There was a really great editorial by Rhode Island State archaeologist Tim Ives in the Providence Journal in 2014 that kind of discussed a lot of these issues. One of the main things to keep in mind is that a lot of these complexes are in kind of multi-use recreational areas and in the forest. So just make sure to follow the signage and keep an eye on children if you go near cellar holes. And then also there are structures that are on federal and state lands, so that some may in fact be protected archaeological sites. So just to keep an eye on any suspicious activity. And I did want to note that if you are curious, LiDAR is available in 3 of the southern New England states for the entire state. I had to modify this slide because my old slide did not have all of the new data sets that have come out. So this is the current state of all the LiDAR data in Rhode Island, Connecticut, and Massachusetts. So you can go to any of these websites to download the data and work with it. So that is all I have for you today. Here I try my best to do the citations, so if you were interested in something, you could look at it. So that is all I have, and thank you. I will take any questions.
Thank you, Kate, Dr. Johnson. I have a few already coming in. One is, what kind of software do you use in this process?
Right, so most of it is GIS software, so I use ArcMap. There's also an open source version called QGIS, which you can work with. Typically, it depends on how down and dirty you want to get with the data. If you are downloading the actual point clouds, that will be an LAS file, and you need, ArcMap will deal with them, but you'll need to learn how to interpolate between the points and turn them into a digital elevation model. But ArcMap will handle all of that, and I believe QGIS will also. And that should help you do any of the visualizations as well.
Okay, so I have another question that is a bit of a doozy because it is being asked by a geoarchaeologist.
Oh, no.
So they were wondering if you could talk a little bit more about how archaeological data in terms of scales of generations to centuries are being used to inform climate change, which is measured in larger timescales. Essentially, how is archaeology helping to understand big climate and environment questions with such fine-grained data?
Wow. That question is definitely like far outside of my wheelhouse, but I will attempt to answer it. I think a lot of the focus on the intersection of archaeology and climate is along the lines of like, how can we save our cultural resources from the impending doom of climate change, right? So I know there's a lot of work being done in terms of saving things from flooding and that sort of thing. But yeah, it's far enough outside of my wheelhouse that I unfortunately can't really give a great answer on that one.
No, that's fine.
But I love that question, and I aspire to answer it at some point soon.
Well, excellent. So there is another question. If you map known indigenous land use against the improved versus unimproved colonial land use, what might you see when if you do that?
Sorry, can you say that again? There's a lawnmower outside.
So if you map known indigenous land use from a specific time period against the improved versus unimproved colonial land use, probably directly right after the Europeans arrive, what do you see? Like, I'm guessing what this question is asking is, do you see colonial Europeans using land that Native people had been using maybe for farming and stuff, but had, either abandoned it, been forced out,
Yeah, I love that question. I have not done any land use reconstruction from before 1700 or so. I don't know, maybe someone on the line here knows if there's a good land use, like a raster or a map or something that shows land use from pre 1700. I'm not sure of what reconstructions are available. I have not personally done them. The walls and the charcoal hearths are kind of the easy tip of the iceberg. Like, yes, we see lots of these. Yes, we know they're related to deforestation, so they're easy to use to reconstruct. But I don't know about any pre-European land use reconstructions that we could use as a starting point to compare. But that is a great question, and that would be a really interesting study.
So, okay, well, those were the questions that have come into me. Does anyone else have any other questions? Okay, well, again, thank you, Dr. Johnson, for joining us today. And for all of our viewers, please join us in 2 weeks when we have Dr. Bill Farley, who will be speaking to us about archaeobotany, which is the study of how people interacted with plants. So a good segue from this conversation today about LiDAR and stuff, and land use. So, well, thank you again.
Yeah, thank you, everyone. It's nice to see you, and thanks.
Okay. Well, goodbye, everyone. Hope to have you join us in the future.